Take out the key.
Yeah, I was a major bummed at one point in the night, and then
Or at least
they got the house.
Scott Walker lost.
Oh yeah, that's right. That's the other thing. Some friends that lived in Wisconsin for a while.
Yeah. The friend who lives there, and me and him were like up like watching the results and chatting, and like every time we'd go we'd switch over to the other guy.
Oh yeah.
And switch back to Scott Walker. And then eventually he went to bed, and then at 2 o'clock in the morning, suddenly the Democrat got 30,000 votes.
Okay.
And we parted ways. It's just
All right. So let's pick up where we left off. So remember what we were doing last time? We were doing basically the simplest possible process that can happen in QED, which is one fermion scattering on a different type of fermion, not the same. In that case, if it's the same, then you have two diagrams. But if it's one fermion scattering on a different type, like electron scattering on muons, you have just one diagram. And we worked it out explicitly. And I want to just go back and also work out the cross section and show we can also use this to get something maybe more familiar. Electron-Muon Scattering, maybe no one has studied it before, among us, but probably looked at Rutherford scattering. And so this can be made to be basically the same thing. One of them will be much heavier than the other. We can take the muon and basically be like the nucleus. The only thing muon about it is I called it a muon and drew it as a muon, right? It's just a fermion in there that we're scattering an electron off of. So we could use this to understand Rutherford scattering too. So let me just write down what it is we worked out. So we worked out this spin average matrix, right? So we sum over initial and final spins, then we divide by 4 for the averaging over the initial spins. And at the end of the day, we found this was 8 e to the 4th, p1 minus p3 to the 4th. Then times a bunch of momenta and masses, p2, p4. Sorry. Writing out in the wrong order, but P1, P4, 2, 3, and then minus P1, P3. I wrote this as the muon mass, minus 2, P4, electron mass, and plus 2 me squared, mu squared. So, what did I suggest? Right, this is totally general. This will work at any energy we want. But with the idea that we're going to use this to understand Rutherford scattering, which, by the way, Rutherford is doing this with fairly low energy projectile scattering off the nucleus. So we're going to take the low energy limit. And basically, we'll look at both low energy, but also the case where one of the masses is much bigger than the other. So this will basically be, this is actually a fairly good approximation for electron-muon scattering too, by the way, right? Muon's like 100 MeV, electron's half an MeV. So that's pretty good. So if we do that, let's just add it so we have it somewhere. So we'll have e to the 4th, p1 minus p3, 4th. And basically, well, for me it's easy actually. All I'll just erase the terms with the electron mass. So, all right, so for our simplest possibility, simplest QED process, at high energy, or at high, sorry, at this, heavy muon mass limit, it reduces to just 4 terms, so we don't have to worry about it. All right, so the way to think about this is, this is sort of the hard work, getting the dynamics right. Now the easy part is basically putting in kinematics, which will give you the cross-section. So I think when we introduce cross-sections, I just give you sort of the most general formula. So let me just state some simple and very important ones. I'll use this to get sigma, to get the cross-section. And very important case is just 2 bodies scattering 2 to 2. Let me write it actually in the center mass frame first. So it ends up being 1 over 8 pi quantity squared. So this is basically just from doing, if you remember our general expression, there's always going to be matrix element squared. Then there's also some phase-space integral you integrate over final state particles, with the right kinematic constraints. So basically, just doing that in phase-space integral ends up giving us some pi's, this S factor, which I'll mention, E1 plus E2, which these are 2 of the incoming energies, and a ratio of momenta. So this could be magnitude of either final, either final particle, and this is the magnitude of either initial state particle. And this thing S is important and not something I guess we discussed before, but this is called a symmetry factor for identical particles. So there's an additional basically this is to avoid double counting in our final states. So there's some discussion about this in Peskin. For the most part, for us, it's not a big concern. That's some combinatoric factor to avoid double counting, right? So it's typically going to be something like some 1 over factorial factor depending on the number of particles. So for example, if you had something like A plus A going to B plus B plus 3 C's or something like that, in that case your symmetry factor would be 1 over 2, because you have 2 B's in the final state that are identical, and 1 over 3 factorial. For us, for this E to mu scattering, it's just 1. So it doesn't really matter in our case. But since I want to give you sort of more helpful cross-section formula than what we did before. Before it was, in a sense, the most helpful version, because it solved all possible cases, but it requires some work, right? And you should know, of course, too, besides looking up in Peskin, if you lose Peskin or something, you can always just go to the particle data group, the PDG, and they have these sorts of nice expressions for the cross-section in the center mass frame, in the lab frame, and so on. And that's very helpful. Also in the lab frame, this is the one we'll actually use in our case, because right? They're sort of an interesting frame to go to, right? If one mass is much heavier than the other, I'm also going to go to the low energy limit where the incoming electron is fairly low energy. It makes sense to go to the rest frame of this guy. And we're just going to have the low energy, so also he's not going to move very much. So anyway, in any case, in that case, in the lab frame, heavy mass limit, which means mu much bigger than electron mass, or at least one of the masses is big. Then it's even better, it's just 1/8π mass of the muon quantity squared times this spin average matrix. Okay, there may be some homework coming up where you'll be asked to derive this from that general expression, but it's sort of just rote. So that's why I'm skipping over it. Just do some integrals over phase space. All right, so basically, that's going to be the route we want to follow. Let's see how this turns into a real cross-section and how we can get out, maybe the familiar Rutherford cross-section. I don't know how familiar it is, but it should be familiar. It's something at least that's been known for quite a long time. All right, so in that lab frame, so basically we'll have let me stop using muon or anything like that. Let me just say that the mass here is just some capital M, some big M because it's a big mass. So I have my big mass particle just sitting there in the lab frame, and he gets hit with some incoming energy and momentum, E1, E1. And right, the only thing that happens is he gets scattered out. Heat is going to get scattered out. We're going to work it up. The only thing that happens is the incoming electron, say the incoming projectile, gets scattered off to some angle, and we're going to work in the limit that this thing that got hit is so massive, right, that he doesn't even move. So to be explicit, and so we know also what to insert into our square matrix element, right? Then we just have our P1. Really, I should do vector here when I write down what the 4 vector for the incoming state is. But he's all in one direction, so sort of use notation and just write it like that. And remember what P1 and P2 are 2 incoming momenta, right? One of them is just sitting there. We'll assume it's also just sitting there afterwards. Of course, in reality, what I should do is do the proper expansion. So I have m plus 1/2 mv squared or something, plus some mv here in the momentum part. But we're going to work to lowest order in the speed. And this will be the same energy. The only thing that happens is you get deflected out to some angle. So what's the thing? I erased it, but the thing that's in the propagator for the photon was just that 4 momenta difference, right? This was a T-channel thing. T is defined as P1 minus P3, so we get to do that straightforwardly. The energy part vanishes, but we have 3 vector part surviving, and it's with the minus sign because we have our metric with 3 minus signs on the spatial part of everything. Then we can expand that out. We get E1 squared minus E3 squared plus 2, plus because I have a minus minus, right? E1 vector E3. These are all vectors. So really what I should work with is just one common momentum that stays the same here. now replace that with my better notation. So this will be 2p squared 1 minus cos theta. By pulling out a p squared from the dot product, and now I'm just putting in what's the dot product as a cosine in it. If I want, I can substitute instead this half angle formula. Turn this 1 minus cos theta into sine squared over theta. Sine squared is theta over 2 times 2. So I get an overall minus 4p squared. So okay, that's the thing in the denominator. I had some other factors. I erased it, but you have it. What the other factors in the numerator are of momenta. Remember, it's basically just different dot products of momenta. So the other things we want are P1, P3. That's one of them. Factors in numerator. So what is, say, P1 dotted into P3? So that's, I'm going to keep it as P1, P3 basically for now. So know why. E squared, we know what it is. It's P squared plus M squared. And this is minus P squared cosine theta. Yeah, exactly. So I'll have again, same sort of thing. This will become M squared plus 2P squared sine squared theta over 2. By grouping together the P squared and then M squared just comes along to the right. And those two factors, we have a P1, P2, P3, P4. Right. So those are actually pretty easy to work out because the 0 on the 3 component will give ME for each of those factors. So I have a ME squared, and that's the same thing actually as the other product that we need in the numerator. P1, P4, P2, P3. And the final thing that we need in our numerator is, maybe that's all. So now you can insert all that back into our square matrix element. And we'll get P squared M over P squared sine squared theta over 2. And M squared plus P squared cosine squared theta over 2. Which is nice because then we have everything we need now to insert into the cross section. Right. So we can also rewrite this in terms of alpha if it's more familiar. Maybe I'll just show that you indeed get the correct asymptotic expression 2mv squared sine squared theta over 2, or you take the p squared much less than m squared limit. Right, I think this marker is dying a bit. I don't know if that's legible. Is that readable or should I rewrite?
Readable here.
Is that readable at school of mine?
Yeah, 2mv squared sine squared theta over 2.
Yeah. And the whole thing.
Yep.
That's right. So this is the familiar Rutherford cross section, which overall is going as 1 over v to the fourth. So at the very least, right, it's good our fancy quantum field theory can reproduce this thing known since time immemorial. We take the low energy limit, but it's certainly more general than that, right? We can also go to, and Peskin talks about the extreme high energy limit instead, the low energy limit. You can compare also, the crucial part really to compare with an experiment is not the energy dependence coming from phase space, which is that overall factor in the cross-section expression I wrote from before, but any of the energy and angular dependence that's inside of the square matrix element, right? That's how you could differentiate between, is there a gamma mu there in the vertex, or is it a gamma mu times a gamma phi? That's going to give you different angular and momentum dependence. So that was actually, you can actually compare to experiment electron-muon scattering and really be done. So QED really is the way to go. We'll talk about this a little bit more too, about different tests of QED over the years, but certainly there have been quite a few. Something I mentioned sort of in passing I wanted to focus on for today was decays in QED. There's some conceptually interesting things. So first of all, right, so by itself, so I'm imagining a world where we have just quantum electrodynamics, right? No other interactions, no weak force, no anything. So by staring just at the vertex, you could basically convince yourself that there's no decays that are possible. So let's look at the QED vertex. So I have a photon, and I have particle, antiparticle, something like that. Right? This is good for all of my, and I know exactly what the Feynman rule is for it. But this certainly doesn't allow any fermions to decay, right? I mean, it conserves the whole stuff about the arrows going in one direction and all that, right? It follows from the fact that there's actually a vector current of fermions that QED obeys, right? So I'm not going to destroy a fermion. There's a conserved current associated with the fermion number. The photon can't decay either because it's massless. If it did have a mass, some version, we could talk about that. That would be a good homework problem. What happens if the photon has a mass? Then it certainly could decay if it's kinematically allowed, right? If this was bigger than 2 electron masses, then something like that could happen. But fermions at least are stable, QED, and the photon is stable. But there are still, in the real world, decays that can happen as a result of electromagnetism, in a certain sense as a result of QED. So this basically the loophole to this sort of statement is that composite particles can decay by electromagnetism or by QED. So, for example, probably one that you're familiar with is the neutral pion, pi 9. So it is indicated 2 photons. So what is the pi 9? So he's built up out of particle-antiparticle pairs with some superposition really of up and anti-up quarks and down anti-down quarks. But anyway, what he really is, what I should think of this as coming from in QED is this diagram. Say it's either an up or a down quark, I'll just try. Q is this thing, this bound state that I call a pion. So it's sort of an interesting scenario in the real world in which, you know, decay is happening from a collision, right? So secretly, pions are little particle colliders. They're colliding quarks. So we can, in a funny way, we can calculate the lifetime of a bound state from scattering, from calculating a cross-section. So we can go through and calculate the cross-section for pair annihilation and get out the lifetime. The simplest thing to analyze is not this, though, because if we wanted to do a decent job of describing what pi zeros are doing, then we have a whole other mini lecture discussion about quantum chromodynamics, which we're not going to do right now. So let's make it simpler. Simplest type of decay in QED is positronium. So it's E plus E minus going to gamma gamma. Where you do this at the lowest possible energies, and E plus E minus really forms a bound state, really is a short-lived thing. You could think of it as a type of hydrogen, right? It's the type of hydrogen where I pluck out the proton in the center and replace him with a positron. So that's convenient because we'll have to use some of the information we remember about the hydrogen atom from non-relativistic quantum mechanics, because that'll be the key to doing this lifetime calculation correctly. Okay, so anyway, it's kind of a funny scenario, but I think it's interesting, and it's, you know, it'll illustrate some new conceptual points too. Right? It's funny to think of that decay as coming from a scattering event, but that's really what's happening. So, right, this pseudo-bound state is called positronium. I don't know if I've worried about positronium before, but anyway, that's his name. So, yeah, before we calculate the matrix element for this, which is sort of involved, we can guess at the cross-section just directly. So, yeah, that's another thing I want to try to emphasize in the last couple weeks of the class is ways of getting the answer before you get the answer, you know? Clever ways of, well, basically doing the right counting. You know how it's going to depend on the coupling, because you can count number of vertices, the lowest order for the process, and then just putting in the right dimensions. So let's first guess, I'll tell you, yeah, so this is basically what we're going to do. We're going to guess the answer, which will be correct, and then we'll go through and get it more properly. So let's first guess at the cross-section. So schematically, some cross-section, well, first of all, the zeroth order thing you always have to do correctly is say, put in the right dimensions, right? I can't tell you my cross-section has units of feet or something like that. That's totally wrong. It's not even wrong in a sense. So the dimensions of cross-section are area, right? Or length squared, or in our favorite units, 1 over mass squared, right? So definitely got to have something like that. And roughly, all cross-sections will be some couplings to some power times some masses to some power times some phase space and then times essentially dimensionless things which could be relevant. Things like velocities, right? We're always using h bar equals c equals 1, so things like velocities can appear here, and those are hard to, this is sort of, let me say, this category is basically things that are hard to guess at. Because by dimensions, you won't know. You have to put in some physics to guess the right power of velocity here. So what is our process, right? It's this. So I have 2 powers of E, and I know the cross-section depends on the square of the amplitude. So for me, cross-section has got to be going as e to the 4th. Right? That makes sense. And I'm also going to be doing this at low energies, right? Where I just barely let them come together, right? They even form a bound state for a little while before they annihilate. So the only energy that's going to be relevant is the mass. The only mass scale is the mass of the E plus E minus. Because they're not moving fast, right? I could do this at high energies too. There's, the LEP collider, for example, is colliding these at hundreds of GeV. So we're not in that limit. If it was in that limit, that would be the relevant energy scale. But here, the only relevant energy scale is the mass of the electron squared. So at least I have the right units now, and I know roughly the right scaling. Phase space, typically for 2-body processes, phase space factors go like 1 over some number times pi, 1 over 8 pi, 1 over 4 pi. I'll put 1 over 4 pi because it ends up being the right number, but it's basically up to factors of 4. It's something like that. You have to do the integral yourself. And in our case, it ends up having a velocity dependence of 1 over v. So this, you can't guess by dimensions. So the velocity dependence comes from the fact that for smaller velocity, you basically have a larger chance of interacting, right? They spend a longer amount of time together, the E plus E minus pair, so there's a greater chance for the scattering event to occur. So this comes from greater chance to interact for small v. So this ends up being the exact right cross-section that you get from doing the calculating the amplitude and working out the phase space factor. But that's not enough. So right, this is a guess, but also the correct answer. We'll come back to the more precise calculation. But it's good to do that also just to remind yourself, because when you're in the weeds of doing a trace of some gamma matrices or something, you may forget that, oh yeah, by the end of the day, this has to be 1 over mass squared, and I have a mass to the 4th or something, so it's something wrong somewhere, right? So, right, the other question then is, right, if we got the cross-section now, how do I turn that into a decay? Right, that seems a little strange. So, how do we relate cross-section to a lifetime? Well, let's remember sort of all the way back to when we defined the cross-section. So we were defining cross-section basically in terms of number of scatterings per time. Number of scatterings per unit. Right, which I can think of as rate of scatterings. So this, this is a real, useful experimental quantity. How many times are your guys scattering? And it's controlled by basically the effective area the particles are presenting to each other. That's the thing we call the cross-section. The other thing it depends on is, what's the intensity of your beam? Sometimes we'll call it luminosity, but it's really just a flux, which we can write as a number density times the velocity. So this will have units of something like per centimeter square per second, right? Number of particles going through some cross-sectional area of your beam per second. So that's great, right? I multiply that thing times something centimeter squared, an area, cross-section, right, and I'll get some rate. So this is basically going to be our proxy for the decay, for the lifetime. It's going to be controlled by the number of scattering that I have, number of annihilations, the rate of annihilations, right? So this will be our proxy for the lifetime. But the important thing we don't quite know what to do with. So velocity is whatever the velocity is, but what's the number density? We think of our bound state as presenting some number density, right? So let's make a little Schrodinger model of a positronium, or a hydrogen, like, you know, this is really hydrogen. So I bring them together, you know, as carefully as possible so they nicely form a little bound state. And then the question is, how long does it take for that thing to collapse and decay in the photon? Well, you know, we know the answer to all the elements to answer the question except the number, right? So let's, you know, just remind ourselves when we were doing back in the good old days of hydrogen atom, right? We would take the proton to be at the center, and then you can work out what's the wave function for the electron as you move away from the center, right? And presumably this is also going to be at the ground state. We're talking about the lowest possible energy where this thing could happen. So, right, I'll put my positron there in the center. And basically what I want to know is what's the electron wave function? So you know, my ground state wave function is certainly spherical. Any weird distortions that would lead to extra angular momentum and stuff. So I have my E minus there, right? And he's some wave function. You know, he's peaked at whatever his typical radius is, some warp radius. But there's some overlap at 0, right? So this tells me the number density of electrons that I get at where the positron is, right? So this is basically the effective number density. And the number density is basically just wave function modulus squared, right? So we know how to do everything. This number density of electrons at the origin, that's just square modulus of ground state wave function for positronium. Does this make sense? I know this is harkening back to things, you know, from last year or something, or maybe before. But yeah, so this is just non-relativistic quantum mechanics. We're just remembering what the wave function is and all of that. All right. So for hydrogen, remember what the hydrogen ground state was. The 1, 0, 0. So remember, right, when I square the thing, I get 1 over number density. So this has to be square root of some 1 over length scale cubed. And only length scale is the Bohr radius. So kind of can guess at what it has to be, but or you can just go back and look in Shankar or whatever quantum mechanics book. So we have this factor 1 over pi a naught cubed. A naught is the Bohr radius, and it exponentially dies off. Right? And the only important thing to remember is this should be well, what is the Bohr radius? But also, it is different. We should use really the proper equation, which we never really did, I think, in Shankar, which is that it's alpha. Usually, you would write it as times the mass of the electron, but really, what we should do is the reduced mass. which becomes the electron mass if it's an electron-proton system, to a very good approximation at least, but it's really m/2 for positronium. So for positronium, this is 2 alpha ME. So, or in other words, twice the normal for hydrogen. So, right, this is the reduced mass. I think we maybe even had some problem in Shankar where you know, do the expansion and reduce mass to the lowest order and keep the correction from the nucleus mass, but anyway. So all that's going to be relevant for us, right, is know what's that number density at the origin. So it's going to be this thing squared. I can forget about the exponential now. So it's going to be this, right, it's 1 over A naught. A naught's 1 over alpha mu, so it's alpha mu cubed, and I have just a pi, because it's square root of pi squared. And that thing, this mu is m/2, and 1 over pi. All right, so basically now we have all the ingredients, right? We can insert back what our cross-section was. So I'll just write it so we have it again. So it's e to the 4th over 4 pi m squared 1 over v. We can calculate the lifetime for positronium. We'll get, from just calculating like this, some number density given by some bound state properties of the wave function times cross-section times v. So the velocity dependence goes away. And once all the dust settles, you can rewrite this also in terms of alpha. So when the dust settles, you get, this is m alpha to the 5th over 2. But certainly helpful to write it in terms of alpha, because then you don't have to write it to some power. Which will give you the lifetime, it's 2 over electron mass alpha to the 5th, which had, when you put in numbers, is like 1/10 of a nanosecond. So it really doesn't want to stick around for very long. But people can make positronium in the lab, and you know, you can actually carry out this little particle collider and verify QED in this way too. But also notice too, right, if we wanted to calculate it from, in a sense from, you know, if we didn't do this stuff about the ground state, estimating the wave function, we would have gotten the wrong answer for the, even just the dependence, right? I mean, the diagram looks something like this, right? Gamma, gamma. All right, naively, I should get that the whole rate is just going as 2 couplings squared, so e to the 4th, or alpha squared. But it's really going as alpha. I really overestimated. If I don't, you know, do all this stuff with the wave function to properly account for that you have this number density coming from the wave function. So anyway, sort of an interesting example how you get a lifetime out of a cross-section. So now let's go back and actually do the calculation a little more carefully. How do we get this cross-section? Remember, we just guessed this from phase space and dimensional analysis sort of. So now let's try and do it using our Feynman rules. questions about this schematic derivation? All right, so now let's do it by assignment. All right, so we have two diagrams. One is T channel, one is U channel, and we'll call this 1, 2, 3, 4. And that guy's momentum is Q. And 1, 2, 3, 4. And there's only one mass to worry about, right? Mass of the electron. All right, so let's do, what's the first diagram? I have two powers of the coupling, so I'll pull that out. And I also know what the momentum will be there. The P1 minus P3 squared, and minus an electron mass. So I have an incoming antifermion, right, which is a V bar, momentum 2. And he meets the vertex with the photon with momentum 4. Will come with a polarization vector, epsilon 4. But also a factor of gamma 4 from the vertex, so I abbreviate them both there with an epsilon slash. And now from the fermion momentum, fermion propagator rather, right, I have one part that I always have, which is the same for scalars and fermions, but then the other part, which is special to fermions, which in this case is P1 slash minus P3 slash plus M. And now I'll have another vertex, so and also another polarization vector. I'll get an epsilon 3 slash. And now the only thing left is to close it up with a U1. And so M2 is very similar. So it's E squared, P1 minus 4 squared, minus M squared. Again, a V2 bar. But now V2 bar means a 3. So it's epsilon 3. And P1 minus P4 slash plus M. Now the only thing left is now I get to this vertex. Now I get to this vertex. This vertex. So I have a epsilon 4 and a U1. So those are the diagrams. Right. This is also a good example of a case where you can't use the Casimir trick. Well, you can and you can't. I mean, so I want to say you can in the sense that when we do this collision, this bound state, oh yeah. You can try and convince yourself from right in this composite sort of state where we have this collision happening. Right, one thing I have to worry about is basically my my spins. Right, whenever I have two spins coming in, they're either going to be in a singlet state or a triplet state. So remember this thing where we had these two ways of adding angular momentum in quantum mechanics. And it turns out that we have to be in the singlet state. is the special case where we know the spins, where we can't average over spins. Since we're either in the spin singlet or triplet state. So also just to remind us, since we haven't talked about these things in a while, so the singlet state, I'll revert to this old notation, is where you're built up out of the superposition of where one is up and one is down. We have a relative minus sign. And the triplet is called triplet because there are three possible states that are there. So one where you have your up, and one where you're up, down, but with a positive sign between them, and one where you're down, down. So we'll see that to conserve angular momentum, basically, the triplet state, if you're in the triplet state to begin with, you'll have zero probability of decaying into two photons. Have to go to an odd number of photons. So the result's strongly going to depend on which spin state you're in. All right, so now let's start working on putting in some real information into the amplitudes so that they can simplify. So we're going to have these really come together basically at rest with E plus E minus coming together at rest. The two photons come out back to back. So I'll have P1, P00, just with the mass basically. I could do this more carefully and really include some initial speed for him, but and the same for P2. And P3 and P4 are photons, right? So they're going to have, each one will still have the same total energy. So there'll also be a mass I can pull out for them. And let me call the z-axis the direction that the photons emerge in. And they just have to go back to back, so one gets a plus sign and one gets a minus sign. So these are my four momenta for the four initial and final state particles. So that's convenient because the thing in the denominator is very simple then. Right, so it's P1 minus P3. So the energy part will go away. I'll have just a mass squared with a minus sign. And I have another minus sign mass squared just from the propagator itself. So first important thing will be that this thing in the denominator, which is also the same thing as P2 minus, P1 minus P4. This is just minus 2, right? So that's going to help. So how do we simplify the numerator? So the first important simplification in the numerator so by the way, you can already probably tell why it's helpful to try and get good at estimating the amplitude without calculating it, right? Doing it in schematic where you count powers of mass and phase space and all that. Because, you know, when you can basically guess that in a minute, well, it'll take you, half an hour or something to estimate it properly. So it saves certainly a lot of time. So the numerator is going to simplify basically, for one, from just using what we mean by the gamma matrices, what their algebra is. So remember they have this anti-commutation relation is written like this. So I suppressed all the gamma matrices in the numerator before, right, with a bunch of slashes. So let's write basically what this means in terms of slashes is if I have A times B slash plus B times A slash, that's equal to 2 A dot B. So is that clear why that is? Just putting those back in, right? If I wanted to, I could multiply, for example, A mu B nu here, and that would give me this. So why that's relevant is it means, for us, we have things like P1 slash epsilon 3 slash, which is really epsilon 3 slash P1, plus 2 P1 into epsilon 3. And another important thing, so this is where we, of course, choose a gauge, but in the Coulomb gauge, like we talked about when we were reminding ourselves about gauge choices and stuff, in the Coulomb gauge, you have that the temporal component of the polarization vector is just 0. It's purely a spatial thing, and moreover, it's orthogonal to the momentum. It sounds like what you want for a polarization vector, right? One who's orthogonal to the direction of motion. So this means P1, you write it as P1 mu epsilon 3 mu is 0. Right? So this part is 0. So if I want to change the order of the slashes, all that happens is I get a minus sign. There's nothing from that dot product. So my P1 slash epsilon 3 slash is the same thing as minus epsilon 3 slash P1 slash. So one of the first terms that I encounter in my T-channel diagram, we're going to rewrite. So P1 slash minus P3 plus M, all that times epsilon 3 slash. All I'm going to do now is when I want to pull out the epsilon 3 to being on the left. So he does that for free on the mass, so that every time he moves past one of these guys, it flips sign. So now I have a minus P1 slash and a plus P3 slash. And the plus M stays like that. Okay, so this is first important maneuver. Not a simplification yet, but we'll see why it's a helpful maneuver. Basically because now I know what happens when I have things like P slashes and masses multiplying spinors. And the reason I know is because those spinors are plane wave solutions, right? So they're guaranteed to satisfy this simplified version of the Dirac equation of motion, which is just the p slash minus the mass, that acting on a spinner is 0. Right? This was a Dirac equation written for a plane wave. So next, recall that this U1 spinner solves the Dirac equation. So in particular, he's a momentum eigenstate. So if I hit that U1 spinner with a P1 slash minus mass, that's just 0. And I have the P1 slash minus a mass will act on U1, right? So that means, an upshot for us, I'm going to have P1 slash minus P3 slash plus M acting on U1. Oh, sorry, I have a. Yeah, let me write down what we actually have in our amplitude. So if you go back to the T-channel expression, right, this is one of the parts of the amplitude. So first thing is we do our reordering. So I can move the epsilon over. I have epsilon 3, now minus P1 slash plus P3 slash times the mass times U1. And all that I get now, the stuff with the mass and the P1 is 0. So I'll only have a epsilon 3 P3 times the U1 spin. So this is one of the parts of the sandwich in the T-channel diagram. I have a similar, so let me just write down. The other part of the U channel, the analogous thing, instead of P1 minus P3, it's P1 minus P4 plus the mass times epsilon 4 P1. That's going to be, no surprise, epsilon 4 P4 U1. Now I can simplify my amplitude quite a bit. So now a big chunk of it becomes simpler, and also the denominator, remember, is really simple now too. It's minus 2m squared. So let's simplify the amplitudes as a almost halfway point. So my amplitude was e squared over propagator, P1 minus P3, minus squared minus mass squared, but that was minus 2m squared. And it was times P2 bar times epsilon 4. And then times this chunk, which now is just this epsilon 3 slash P3 P1. And the second diagram is e squared over minus 2m squared. P2 slash. And now the only thing is now the epsilons are inverted, and I have a P4 as well. All right, so that's a good simplification. And we also, I didn't emphasize, but right, there's no relative minus sign between the two diagrams. That would happen if I had fermions or something in the final state. But since the T and the U channel are related by this particle exchange, that particle being exchanged is a boson. So I don't get any minus sign. I just add them, which will mean that they interfere constructively. Okay, so I'll also just add them. So I have a minus squared over 2m squared. And everyone has a v bar and everyone has a u. So let me just make one big parentheses epsilon fourth epsilon 3 P3 slash plus epsilon 3 epsilon 4 slash and then mu1. All right. So does this make sense so far? We haven't done anything too crazy. Just remembering some gamma matrix algebra so we can move the epsilon around, and then remember this helpful fact that these are solutions to the Dirac equation. Seems like a good type of spinner to work with. So now an important simplification can come from working out P3 and P4 slash explicitly. So remember, P3 and P4 are what? They're the momenta of the final state photon, right? And we were saying that their momenta are such that, well, they're photons, so energy and momenta are the same, and they're back-to-back, right? They're all along the z-axis. Z-axis is also known as the third spatial axis, right? So this guy was really P3 mu times the gamma mu. So really I have the sum, but the only part of P3 that are non-zero are the zeroth component and the third component. So, and overall the magnitude of the thing was just m. So I get that the P3 slash is just mass times gamma naught minus gamma 3. Minus because, right, whenever I do the Lorentz invariant dot product, I get a minus sign on the spatial components. And P4 is the same, except he'll have a plus sign because his momenta is equal and opposite to the other one, right? Okay, so our expression in square brackets up here in our amplitude schematically, it's just the one directly above. So what is it going to become? So it'll be epsilon 4, epsilon 3, now times the mass, gamma naught minus gamma 3, plus now the other one, epsilon 3 slash epsilon 4, mass, gamma naught plus gamma 3. Now let me start grouping things according to which gamma matrix you're touching. So it helps I can pull out a mass, everyone has a mass. So this will become mass epsilon 4, epsilon 3, plus epsilon 3, epsilon 4, gamma naught, minus epsilon 4 slash epsilon 3, minus epsilon 3 slash epsilon 4, times gamma 3. It's a lot of writing, but at least we're using slash notation. It'd be even more writing if we weren't. So we can also simplify and start putting in some information about epsilon slash. I'll put that over here. Alright, so let's also what is epsilon slash. Okay, so it's definitely epsilon not gamma naught, epsilon vector dotted into gamma vector. But in the Coulomb gauge, like we're using, this guy is 0. The temporal component of the polarization vector is 0. We can also remember a convenient representation of the gamma matrices in terms of Pauli matrices is 0 sigma I minus sigma I is 0. So I can write this as, this is just minus epsilon gamma, or in other words, pulling out the overall minus sign, sigma dotted into epsilon, 0 minus sigma dotted into epsilon. So that's what epsilon slashes in general. And then I have a bunch of products of epsilon slashes. So I can do things like epsilon 3 slash epsilon 4 slash. It'll just be two of these multiplied together, so you can carry out the multiplication, and you'll get something proportional to the identity. Get sigma epsilon 3 times up sigma epsilon 4, 0, 0, and sigma epsilon 3, sigma epsilon 4. So it turns out the reason we wrote it like this is because there's a helpful expression that I know we did actually in Shankar. I guess it's been a while, so you probably don't remember. There's a helpful expression whenever you have something like this. You have sigma dotted into A times something like sigma dotted into B. You can rewrite this in terms of dot product between A and B and cross product. So this goes all the way back to Shankar. It's one of those lesser used Pauli identities, but one that comes up now and then. Right, this is just A dot B and plus I sigma dotted into A cross B. And the reason that's useful is that now when I'm combining, doing the sum of the product of two epsilon slashes or the difference, I'll have either just the dot product part surviving or just the cross product part. So then one gets from, basically we're going to substitute, we're going to write down some nice expressions now for these two parentheses, these two different combinations of epsilons. So we have epsilon 4 slash epsilon 3 slash plus epsilon 3 slash epsilon 4 slash. That becomes just minus 2 epsilon 3 dotted into epsilon 4. And epsilon 4 slash epsilon 3 slash minus, that's equal to 2I epsilon 3 cross epsilon 4 times this matrix of the Pauli matrices, just to account for this structure there. All right, so that's helpful, although it looks weird, maybe, remembering some old stuff. Sometimes this is sort of a grown-up version of the Pauli matrix, guy who's put into a big, he's multiplied by the identity, But anyway, sometimes this gets its own name, called capital sigma. I guess to remind us that it's really related to lowercase sigma. So we can put that back into the amplitude. Right. So remember what we had in our amplitude, right? We had this stuff p squared over mass squared. I think I just forgot something. Oh, yeah. Right. Right, so one of the masses cancels because we had a mass coming from those p slashes. So this becomes p bar, v bar, and u bar. The thing we were simplifying was just that thing in square brackets, which using this identity becomes epsilon 3 divided to epsilon 4 in and out plus I epsilon 3 plus epsilon 4 divided into big sigma times gamma 3, all that times u1. So this is still actually totally general from the point of view of the incoming spinners. We haven't imposed any information yet about the singlet structure. So far, this is totally general with respect to spins. So we'll need to construct a singlet amplitude. So we'll find out what is a singlet amplitude. Well, it's definitely, we're just going to use the information from the addition of angular momentum stuff to build it up as a properly normalized thing. So that's what the square root of 2 is times amplitude where 1 is up and 1 is down minus where 1 is down, 1 is up. So maybe a good time to pause now and pick up next time. But what we'll do now, so let's remember too that this is a 4-component. Both U's and V's are 4-component objects, right? We need all that 4-component information because we have an electron and a positron, and either of them can be up or down, right? So that's why we have 4. So U only basically has interesting spin up or spin down stuff in the first 2 of those 4 components, while V has all the spin information in the bottom 2 components. So basically that's what we're going to impose next time is say, let's say the electron is in the spin up configuration, positron is in spin down, then we'll be able to get what this up-down configuration is. And we'll find that the up-down configuration is equal to minus of the down-up. Which also will tell us why, if we had a plus sign here, why we would get 0. So that's why if you're in the triplet state, there's no decay. You have to go to more photon final states. But yeah, I think that's there's still a significant amount of stuff to do once we start bringing in that spin information. And remember what we know we have to get at the end of the day. So before we were guessing actually at the cross-section rather than the amplitude. But the cross-section, if you go back to it, the cross-section had all the right dimensional information in the prefactor, not in this. This thing basically only contained epsilon and some numbers. we don't know what the numbers are, those are dimensions. But sorry, not epsilon, the electric charge E. So at the end of the day, this has to be going as, E squared times basically some leftover numbers which we're not able to guess. But the information about spin and polarization vectors, all that's going to be gone if our guess at answer was correct, right? So there's still a significant amount of work left to do to see that all that follows through. That, basically taking into account the correct spin information for the incoming fermions and for the polarization vectors for the outgoing photons. So we'll do that next time. And so next Wednesday, so you'll have a long weekend, right? Long enough to work on a nice long QED homework problem. We'll work out the amplitude and do the Casimir trick to get the spin average amplitude in a sort of fast way, and then use that to get out the cross section too. So it'll be good practice for practical applications of QED. So we'll finish this up next time and maybe say a little bit about renormalization and quantum electrodynamics. All right, well, so have a good long weekend. See you guys Wednesday.
No, it was a long weekend.
Wow. I have to come in for lab prep.
Oh, you do on Monday? If he still does that.
Yep.
When I did it, Ryan McClellan was doing one of the labs and he emailed me and said, don't come in.
Because you had to drive.
Yeah. He said, Vern can't legally make you come in.
Huh?
Vern can't legally make you come in.
Yeah.
But he did it.
That is good, actually.
Also, some of those are so easy. But it's like,
Well, like I did all of them last year too.
oh, yeah. I don't know what I'm going to do next semester.
Are you not grading anything now, or are you grading?
No.
Maybe you'll get lucky.
What about Brazil?